And when you are driving on a highway, when you look outside your car windows, you see everything is moving past you, right? That's relative motion. And same idea, if I'm walking from here towards to the back end of the classroom, and the student sitting here look at me is like I'm walking towards him. But if you're sitting over there and you look at my position, I'm looking at a totally different direction respect to your observation. So we're going to talk about how to use vectors, to describe relative motion. So let's first look at an example. If we have two particles, particle A is at that location, particle B is at a different location. If we are inside of a Cartesian coordinate system with origin O right there, and if we're standing at point O, the position for A and B are very straightforward, right? We have position vectors to describe position of a particle. Let's use different color. Connect point O and point A, add an arrow that will give you position vector A, right? If you want to describe the position of particle B, connect origin to particle B, that's your RB. Once again, we're talking about position vectors. They're all vectors. But what is the relative position of B with respect to A? In other words, what happens if you're standing at point A looking at point B? What is that position vector? We can draw that very easily, right? It's just this vector pointing from A to B. This is the relative position vector. Let's call it RB/A. So here is important, this RB/A, it's a position of B with respect to A. Or you can see it's a position of B observed from point A. So here the wording is important. Since this is a position of B with respect to A, that's why we have this B/A, right? RB/A and RA/B are totally two different things. Don't mix them up. So RB/A only means it's a position of B with respect to A. What if I have another vector that is RA/B? What's that mean? That means it's a position vector of A with respect to B. Okay, keep that in mind. All right, from what we learned in vectors, we know we can add the head and the tails of the vectors together, right? So here we have this vector RA. This vector can add this vector, and the result would be this vector RB. That's something we learned from vectors a long time ago, probably. So we learned that RA plus RB/A equals RB. And we can rearrange this to write out what is RB/A. So RB/A can be written as RB minus RA. So now we have our first equation that's a relative position vector. And here, I want you to pay extra attention to my notation here. Since here I have RB/A, RB/A. So B is the first and A is second. That's why you inside of this calculation have B at first and A second. That's very important since here's a minus sign. If you flip the order, the result going to be different, right? If here I have RA slash B, then the calculation should be RA minus RB. So that keep in mind, it's something very tiny, easy to, but it's very easy to forget. Okay, this is our position vector for relative motion. And how about velocity? Can you guess what velocity would look like for relative motion? VB slash A. VB slash A compared just to the position, it's same deal. It's equals VB minus VA. For acceleration, AB slash A equals to AB minus AA. Yeah, remember the definition of these three equations. Those are for relative motion. Okay, now let's look at an example. Let's see how to apply this. So this is example from your textbook 1D1. And I need a volunteer to read that example 1D1 for us. I see Gary has a book. Do you mind read that for us? 1D1.
Speed is increasing at a rate 10 kilometers per hour. At this instant, A and B are traveling in the same direction. No one find the acceleration of the passenger in car A to car B.
Okay, thank you. So we know two cars, car A and car B. We know both their speed and acceleration. So car A is slowing down, car B is speeding up. And what we want to find is the relative acceleration. Car B is moving along a path. And the path has a radius of 500 meters. Car A is moving on a straight line. Yeah. So this is everything we know. And I want everybody look at the question here. What acceleration does a passenger in car A observe for car B? So I have a question for you. I want you to discuss with your neighbors to figure out what acceleration are we looking for here? Are we looking for RA/B or AA/B or AB/A? Okay, I'll give you 1 minute, talk to each other, figure out which one would you use. Which one is the correct answer? Okay, so how many of you are thinking we need to find out what is AA/B? Raise your hand. And how many of you think we're actually looking for AB/A? Raise your hand. Okay, who's right? Who's the winner? Right, in this problem, we're looking for AB/A. Yeah, here's all about language, how wording here. All right, the one trick to kind of help you to kind of get this right is to look at the question, find out who is the observer. All right, in this case, who is the observer? Car A or car B? A or B? Well, you guys are Americans and this is all English and you can tell me. A or B? A, yes. So that's first thing to figure out. If you know who is the observer, put the observer second. So slash, what is following the slash? It's observer. Okay, that's kind of a trick to help you in the future. If it doesn't tell you it's A or B or A, you can use this find observer to identify should that be AB/A or AA/B. All right, does it make sense? Okay. All right, now let's look at this question. What we know? We know VA, we know speed of A, it's 80 kilometers per hour. Well, here we have multiple different units. We have meters, kilometers, hours. All right, let's convert everything to meters and second to make our life easier. So let's first convert 80 kilometers per hour to meters per hour. Okay, that's something you should always check before you do a problem. Make sure all the units are the standard units. So 80 miles per hour, it's about 22.2 meters per second. The direction of that speed is pointing down. Also, we know acceleration. Now, let's change the word here. The rate change of speed. So we know car A is speeding up at this rate, which is 10 kilometers per hour square. And that tells you actually the rate change of speed of A is, convert that to meters per second square. It's about 7.7 times 10 to the negative 4 meters per second square. Yeah, now you realize the rate change of speed, v dot, it's super important, right? Previously, we used that to help us determine is the speed of a particle decreasing, increasing, or constant. In this example, we use that speeding up or slowing down to determine the sign of v dot. Since for car A, it's speeding up, so we have positive v dot, right? And for car B, same deal. VB is moving at a speed at 50 kilometers per hour, which is about 13.9 meters per second. The direction is pointing down, right? Both cars moving at same direction at this instant. And the rate change of speed for car B, it's negative 10 kilometers per hour square. That is your VB dot, which is 7.7 times 10 to the negative fourth meters per second square. Okay. And in this example, we have two cars, two particles. Let me tell you, we want to use path coordinate system. Remember, path coordinate system. And my question for you is, how many path coordinate system we need to use for this problem? Think about where's the origin for path coordinate system. Where? Yeah. Can you use one path coordinate system to describe motion for two cars here? No. The reason is, if you want to just use one single path coordinate system to describe motion for car A and car B, where are you going to put the origin of that path coordinate system? The path coordinate system must be on the particle, right? You have two particles, you can only choose one. So since here we have two particles, theoretically we need to have two path coordinate system. One is for car B, one is for car A. Okay, now how would you draw the direction for unit vectors? Let's see, car B. What's the direction for ET? Use a finger pointing to the direction of ET. Show me your fingers. Direction of ET for car B. ET is tangential direction, should always pointing to the direction of motion. So it's pointing downwards, right? Where's EN? Pointing to the center of curvature. You need to memorize this. This is E, let's call this ETB. And this is our ENB. Okay, now let's look at car A. How would you draw the unit vectors for car A? Use your finger pointing, where's the direction for ET? Yeah, it's the same direction. Let's call this ETA. Now the tricky part is, where the heck is our ENA? For car A, do we have an ENA? The normal direction. Why is that? We're traveling straight line. What does that mean? Yeah, zero. Why that's zero? What's the radius of curvature for straight line? Zero or infinite? Infinite. Don't mix that. If you're traveling at a straight line, the radius of curvature is infinite. If that rho is infinite, when you do v squared over rho, that's on your En component, that will give you zero. So for car A, we don't have anything on En direction. Okay. If right now I want you to do a coordinate system conversion between this path coordinate system and this path coordinate system. What's the relationship between ETB and ETA? What? Say that again.
They face the same direction.
So, what's your answer?
They're the same.
They're the same. Yes. If I ask you to do a coordinate system conversion, and here ETB and ETA would be the same. They're pointing to the same direction. There's no angle between them. Well, if you want to build triangles, you can, but there's no triangle there. So they equal to each other. And how about, what if I change the direction of car A? If at this moment car is moving up, then what's the relationship between ETA and ETB? Equal and opposite. Yes, that's important because in the future, I don't remember which homework, we're gonna have something like that. Maybe it's in your this coming homework, which is due on Monday and Wednesday. Yeah, keep that in mind. Okay, now we have everything. We figured out the direction of ETA and ETB. Let's look at what is the relative velocity between A and B. Let's do VB/A. Okay, now one question for you. If I write velocity as VB/A, I want one of you translate that into English. What does that mean? VB/A. Speak louder. So
the velocity B with respect to A.
The velocity of car B with respect to A. Yes. So A, remember that slash, that thing, it's an observer. So all you can see, it's the speed of B observed in car A. That works too. Okay, so what is VB equal slash A? Equals what? From the definition, equals V what? We know it's the difference between two velocity. Should be VB come first or V come first? VB come first and VA comes to second. All right, what is VA? Yeah, 22.2. That's ETA minus, wait, sorry, my bad. VB equals 13.9, right here. VB 13.9 ETB minus 22.2 ETA. Since ETA, ETB are the same thing, so we can do the vector operation, right? You will end up with a negative number, which is negative 8.3 ET. Let's just call it ET, use ETB. The units meters per second. So that is the relative velocity, VB/A. Okay, now let's look at acceleration, AB/A. AB/A equals AB comes first and A it's second. Oops. What is acceleration of car B? What is acceleration for car B? Car B is there. What coordinate system are we looking at here? Path. Then what is acceleration for car B? You can have a pick on your quiz. What's there? Come on, guys. What is on your quiz? Second problem. V dot t plus v squared over rho en. Yes, that's the acceleration. Define definition of acceleration under path coordinate system. So here for V A, V B, it's V B dot ET plus V B squared over rho, let's call it rho B, En. Let's call it ETB, ENB. That's the acceleration for car B. Minus acceleration for A. Yeah, A is also inside of this path coordinate system with VA dot ETA plus, you can write this as VA squared over rho A ENA. Yeah, feel free to write that out if you want to, but since this is rho for A, straight line, so that is infinite large, so the second term goes to 0. So what we end up with, it's an expression with VB dot minus VA dot as your ET component, ETB, plus VB squared over rho B, EMB. That is the relative acceleration of B with respect to A. Yeah, if this is the symbolic solution, if this is on your homeworks or exams, that's a symbolic solution I like to say. So highlight that, then you can plug in numbers. Okay, I made a mistake here. Who can tell me where's my mistake? If this is how you highlight your answer, I would take points off. Why? Yes, units, and what is the other thing? Vector symbol, yeah. The unit is meters per second square, add the vector notation there. All right, next you can plug in numbers. And you end up with negative 1.5 times 2e to the negative third ET plus 0.38 something En. Okay, that's how you find the relative acceleration. All right, that's all we have today. And remember, we have homework, 2 homeworks due today, and another homework due on Monday. Right. Office hour today from 1 to 2. Your last chance to ask question this week. Okay. Have a good weekend. I will see you on Monday.